As a part of our online class, we are going to begin with the chapter Magnetism. So this is the first video about introduction to magnetism. So you all will be familiar with the term magnetism. It is the property by which certain material attracts metallic substances like iron, nickel, cobalt, etc. So a material that shows the property of magnetism is known as magnets. So there are different types of magnets you are basically familiar with, for example horseshoe magnets, bar magnets, etc. And we are using bar magnets in our laboratory experiments. So suppose you have a bar magnet. So bar magnet somewhat rectangular in shape. It will have two poles, a north pole and a south pole. So if one pole is north pole, obviously the opposite pole will be south pole, and we know that the magnetic lines of force are pointing or are directed from north pole to south pole. From north pole to south pole. So this is the magnetic field lines of a bar magnet. We have already studied this. And a bar magnet, or every magnet, let it be any kind of magnet, they have a north pole and a south pole. So how do we determine if a magnet is having which side is north pole and which side is south pole? How are we able to detect which side gives us north pole and south pole? So in order to understand that, we have to study certain properties of magnets. So some of the properties are given in your textbook. This is just an introductory video to magnetism. So one of the properties, when you suspend a bar magnet freely, suspending freely. What do you mean by suspending freely? അതായത് ഒരു കയറുമേൽ കെട്ടുക, ആളെ ഒരു കയറുമേൽ കെട്ടിയിട്ട് സസ്പെൻഡ് ചെയ്ത് വെക്കുക, തൂക്കിയിടുക. So you suspend a bar magnet with the help of a rope freely without any external force except gravity acting on it. So what happens? And you are suspending a bar magnet like this, and it will start rotating like this, and finally it will come to rest in a particular direction. For example, always a bar magnet will come in a direction such that one end will face the geometrical south pole and the other end will face the geometrical north pole of our earth. അതായത് ഒരു ഭാഗം എപ്പോഴും നമ്മൾ ബാർ മാഗ്നറ്റ് നമ്മൾ ഫ്രീലി സസ്പെൻഡ് ചെയ്യുകയാണെങ്കിൽ ഈ ആൾ ഇങ്ങനെ ആ കയർമേൽ കിടന്ന് റൊട്ടേറ്റ് ചെയ്യും, എന്നിട്ട് അതൊരു പെർട്ടിക്കുലർ ഡയറക്ഷനിൽ അലൈൻ ചെയ്യും. എപ്പോഴും എങ്ങനെയായിരിക്കും അലൈൻ ചെയ്യും? ഇറ്റ്സ് ഓൾവേസ് അലൈൻ സച്ച് ദാറ്റ് വൺ ഓഫ് ദി ഡയറക്ഷൻ നോർത്തിലേക്ക്, the other direction point towards the south, and the direction of the bar magnet which points towards the north is known as the north pole. അതായത് നമ്മുടെ എർത്തിന് ഒരു നോർത്ത് പോൾ ഉണ്ട്, ഒരു സൗത്ത് പോൾ ഉണ്ട്. എർത്ത് ഹാസ് എ നോർത്ത് പോൾ ആൻഡ് എ സൗത്ത് പോൾ. നമ്മളൊരു മാഗ്നറ്റിനെ ഫ്രീലി അലൈൻ ചെയ്താൽ അല്ലെങ്കിൽ ഫ്രീലി സസ്പെൻഡ് ചെയ്താൽ, വിച്ച് പാർട്ട് ഓഫ് ദി ബാർ മാഗ്നറ്റ് പോയിന്റ്സ് ടുവേർഡ്സ് ദി നോർത്ത് ഗിവ്സ് ദി നോർത്ത് പോൾ ആൻഡ് വിച്ച് പാർട്ട് പോയിന്റ്സ് ടുവേർഡ്സ് ദി സൗത്ത് പോൾ ഗിവ്സ് ദി സൗത്ത് പോൾ. ആൻഡ് ദി മാഗ്നറ്റിക് ലൈൻസ് ഓഫ് ഫോഴ്സ് ആർ ഓൾവേസ് directed from north pole to south pole outside the bar magnet, and from south pole to north pole inside the bar magnet. That means the magnetic lines of force are closed. So when it comes to when we compare the magnetic lines of force along with the electrical lines of force, suppose you have a positive charge here. We have already studied that positive charges diverges and negative charges converges. So we know that whenever there is an electric field is present, the electric field direction is from positive to negative. Similarly, whenever you place a magnet somewhere, the magnetic field lines direction is like this. So some of the properties of magnets is that magnets have attractive property. They attract certain metallic materials. When they are suspended freely, they align along the north-south direction of the earth. And force between the poles. So when we come to the magnetic force due to a magnet, that means when we have two magnets, suppose you have two bar magnets placed like this, and one bar magnet will have north pole, other south pole, north pole, south pole. When these two bar magnets are brought together, that means north pole and south pole attract each other, whereas when south pole is brought to the south pole, that means like poles repel, and unlike poles attract. This is similar to the behavior of charged particles. For example, when you bring two positive charges together, they repel each other, and when you bring two negative charges together, they attract each other. So we can compare magnetism with electrostatics and study, because there are many cases in which magnetism shows a behavior in which we can compare the behavior of magnetism with the behavior of charged particles in electrostatics. So like poles repel and unlike poles attract each other. Now, just like the electrostatic force, the magnetic force also has inverse square law of magnetic forces. That means whenever you bring two bar magnets or any magnets, like we are taking bar magnets because you are familiar with bar magnets. So whenever you bring two bar magnets together, you have this pole. Suppose the pole strength of this pole is M1 and the pole strength of this pole is M2. Then what is the magnitude of force of interaction between these two magnetic poles of two magnets? So the force between these two poles is directly proportional to the product of the magnetic forces and magnetic strengths, and the force is inversely proportional to square of distance between them. Just like in the case of electrostatics, that is F is proportional to Q1, Q2, F is inversely proportional to R square. So the total force F is proportional to M1 M2 divided by R square. So in order to replace this proportionality with equal sign, we have to introduce a constant here. So in this case, we used F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. But when it comes to the magnetism, in magnetism we are not using epsilon 0. The constant that is used in magnetism is given by F is equal to mu 0 divided by 4 pi M1 M2 divided by R square. So this is the magnitude of force that exists between two magnetic poles of strength M1 and M2 separated by a distance R, where mu 0 is known as, mu 0 is known as permeability of free space. So this is the force of attraction when it comes to free space. Suppose you are using any other medium whose permeability is mu. Then the force of interaction becomes F is equal to mu divided by 4 pi M1 M2 divided by R square, where mu is equal to mu 0 into mu R, where mu R is the relative permeability. So whenever any other medium other than free space, the magnitude of the force is given by F is equal to mu divided by 4 pi. Whenever you see mu 0, epsilon 0, etc., you have to understand that particular term, that particular force corresponds to a free space. Now we can hear that repulsion. So in order to understand whether a material is magnet, you have to check whether that material repels with any other thing. So attraction is not a sure test of magnetization. Whenever something attracts another material, for example, when you place a magnet here, a magnet attracts a metal. When you place a magnet along with metal, the magnet attracts metal. Since magnet attracts metal, we know that this is magnetic, but metal is not magnetic. But whenever a magnet is brought near to another magnet, we can say that they might attract or repel. So a repulsion is found only between two magnets. That means whenever there is a repulsion is present, we are sure that the material is magnet. But whenever you see attraction, you cannot say that both materials are magnets, because one of the material may or may not be magnet. So if you are asked that why is repulsion a sure test of magnetization, it means that whenever two materials repel, it is sure, whenever they repel each other, it is sure that both of them are magnets. But whenever they attract, we cannot say both of them are magnets. Now we are going to talk about what is a magnetic dipole. Just like an electric dipole, we know that electric dipole is two equal and opposite charges separated by a very small distance. Similarly, magnetic dipole is a it consists of two unlike poles of equal strength separated by a small distance. For example, uh, there will be two poles. Suppose two opposite pole means north pole and south pole. Two opposite poles are separated by a very small distance 2L and they have same magnetic strength. Then they are said to be this arrangement is known as a magnetic dipole, just like an electric dipole in which a positive and negative charge is separated by a distance of 2L. Just like electric dipole moment, we have magnetic dipole moment capital M is equal to strength of the one of the pole, because both the strengths are same, M into the distance between them, that is M into 2L is the magnetic dipole moment of a magnetic dipole. So some examples of the magnetic dipoles are, a bar magnet. Bar magnet itself is an example of magnetic dipole. Then atom, because atom consists of a central nucleus around which an electron is continuously revolving. So it also produces, we will discuss about that, and a current carrying circular loop or any closed loop that carries current in anti-clockwise or clockwise direction. They also produces a magnetic dipole. We will discuss about that. Now current loop as a magnetic dipole. What do you mean by a current loop as a magnetic dipole? We have already said that a closed current loop, whatever be the shape of the current loop, let it be square, any circle or any shape. Suppose it is carrying a current in a particular direction, then this current loop acts as a magnetic dipole. Magnetic dipole means it has a north pole, it has a south pole. It has two poles are there separated by a very small distance. Then how can we say this current carrying wire acts as a magnetic dipole? Listen here. When this current is carried in clockwise direction, suppose you have a loop like this, When we look from this side, that means when we stand here and look from this side, we can see that the current is in clockwise direction. If the current is in clockwise direction, then we can say that this particular face of the loop acts as the south pole. Now if someone sees the loop from the back side, when this person observes this loop, he can see that the current is flowing. According to him, the current is in the anti-clockwise direction. That means that when this person looks from the backward direction, he sees the loop like this, and the current will be flowing in anti-clockwise direction. So when this side acts as the south pole, the opposite side acts as the north pole. In order to understand that, you can draw north like this, N like this, that is anti-clockwise current, that means that phase acts as north pole, and clockwise direction current, if the current flows in clockwise direction, that part acts as south pole. So this is the current loop as a magnetic dipole. Since the current carrying loop acts as a magnetic dipole, we can say that it also has a magnetic dipole moment. So how to find the magnetic dipole moment of any loop? So this is a square loop. Suppose you are taking a circular loop, then also if the current is flowing in anti-clockwise direction, this particular side of the loop acts as south pole, and someone sees from the back side, if someone is observing it from the back side, the back side will act as a north pole. Now the magnetic dipole moment capital M for a circular loop is given as the product of current I into area enclosed by that particular loop. For example, if R is the radius of the circular loop and I is the amount of current flowing through it, then M is equal to the current I into pi r square. Now when it comes to the square loop, if it is a square loop of side L, then what is the magnetic dipole moment? If it carries a current I in the loop and its one of the side is given by L, it's a square loop. Then what is the area of the square? This area of the square is given as L square. Then magnetic dipole moment of the square loop carrying a current I into L square. As for any case, the magnetic dipole moment of a circular loop or any current carrying loop is the product of current through that loop into the area of that particular loop. So this is the introduction to the chapter magnetism. And one more point is left, that is the existence of magnetic monopoles. We have already studied that electric monopoles exist. For example, you have separate positive charges, separate electric charges. But when it comes to the case of magnetism, you cannot say that a north pole exists independently or south pole exists independently. Northum southum separate ആയിട്ട് ഒരിക്കലും exist ചെയ്യില്ല. For example, suppose you have a bar magnet. It will have a north pole and a south pole. Suppose you cut here and you get two pieces. We will get two pieces of bar magnet. If you cut this into half, then what will happen? There will be a south pole in this side. There will be a north pole in this side. But whenever you cut a bar magnet, you will not get north alone or south alone. What happens the moment you cut it? A south pole is formed here and a north pole is formed here. That means magnetic monopoles do not exist. Just like electric monopoles or electric single charge, just like single positive charge or negative charges, single north pole or south pole do not exist. So this is the introduction to magnetism, and tomorrow we will talk about Earth's magnetic field, its sources, and other important terms regarding magnetism.